So I'm looking at section 7.2 of your book, and this is looking at problem solving with algorithms, and we've looked at sort of this methodology of Polius, and now for the rest of the chapter we're going to be developing algorithms, and we're going to be expressing those algorithms using pseudocode. So we understand that an algorithm is a sequence of, well, I'll go ahead and I'll just go ahead and write it. An algorithm is a kind of a finite sequence of steps that you go through to solve a problem. Let me actually see. Here we go. An algorithm is an unambiguous, did I spell that right? You know, you guys can forgive the spelling, I hope. It's an unambiguous sequence, right, of instructions for solving a problem in a finite it says amount of time, but I'm going to write number of steps. And using also finite data. So that's kind of, it's in a little box in your book somewhere. It's worth remembering. I think keywords are unambiguous. This is why we don't use English for explaining algorithms, because too many things in English are ambiguous, and you know, the sequence, so the order matters, and you need a finite number of steps. So you can't have an algorithm that just says add an infinite set of numbers together and then do this. So you can't possibly do something an infinite number of times. You know, so you can't say add 1 plus 1/2 plus 1/4 plus 1/8 and so on, because that would be an infinite series. We know that the solution is 2, but it would take an infinite number of steps in order to reach it. So this is not a good way. This is not a good algorithm for calculating whatever that would be, right? Because it would never stop. Although we do have algorithms that use series like that, for instance, to calculate pi. But it needs to happen in a finite number of steps, and you need to use a finite amount of data. I feel like that's implied here. So these algorithms, they could be specified different ways. You can use plain old English. You can use flowcharts. Your book does not talk about flowcharts, but a flowchart has symbols like this, which represent a condition. So in here you might write something like is A greater than B? And if that has a result which could be true, then you have a branch coming out that says maybe yes, and a branch coming out that says no. And the idea is you've got these kind of arrows, and we have boxes that represent a process, which would mean do something, right? So these would be kind of statements, and this is branching conditions. And if you want to do one thing after the other, you chain them like that. This kind of a diagram is called a flowchart. I don't see them taught too much anymore, but I think sometimes it's going to be useful to understand that we can kind of draw this, and in order to imagine how you can express algorithms like this among some other ways, and I feel like sometimes seeing this kind of picture is going to be good for helping us understand some of these control structures we're going to see in pseudocode. So control is imagining like you have a current thing that you're doing, and as you move through, these control structures determine which path of execution you're going to follow during a certain computation. And control structures are things like looping back, or branching, where you can either go one way or the other. So let's look at section 7.2, and that is looking at, if you forgive me, the projector itself is getting in my way. It's looking at something called selection. And they have an example. So the idea is expressed here in pseudocode. I always number my steps in pseudocode. So we imagine that we've got some algorithm that's supposed to determine how to dress, right? So maybe this is some sort of a procedure. Determine how to dress. And the first thing that we're going to do is we're going to sort of write out, enter the temperature. So in your book, they always assume that input comes from asking the user a question like this, and then read in a variable. So we're going to call this variable temperature. And the next step, I'm going to write it in red because we don't really know how to do this next step yet, which is determine how to dress. Unfortunately, that's the main thing that we were trying to solve to begin with. So this sort of stuff is kind of boilerplate. It doesn't really help us narrow down how to solve the problem. We need to drill down on that. So I'm going to flip the page and I'm going to drill down on that part. So determining how to dress. Now, I just want to point out that this kind of process of specifying at a very high level how we want to do things, and including steps that we don't know how to do as part of this sort of main logic, is part of the process that we use to develop good algorithms, right? So even though you don't know how to do it, you kind of break it down into smaller pieces, and now, assuming that we have a variable called temperature that we can use, now how do we determine how to dress? So we've just added a little bit of information here. So in order to determine how to dress, we're going to introduce a set of statements called if, then, and else. So I'm just going to write that up here. If, then, and else. And the way that they work is like this. In pseudocode, it's similar to English, although there may be some subtle differences. So in pseudocode, you say if, and then you must specify a condition, usually in parentheses. So if, in this case we could say if the temperature is greater than 90. So this is a condition. It's kind of the thing that would live inside of a diamond in a flow chart. It should be something that evaluates to either true or false, right? So if the temperature is greater than 90, then we're going to produce some output. We're going to say wear shorts. Great. So this block of code here is the bit that you execute when the temperature is greater than 90. For output in a flowchart, sometimes you make these things diagonal, and then you would just say wear shorts. Right? Now, if temperature is not greater than 90, then you come down here and you execute the else block. So this if and this else are both part of this sort of same selection construct. And you can chain multiple else's together. So this condition will happen only if the condition is true, and you put an else, and then this condition will happen only, or this block of code will happen only if the condition is false. So line 4 would be, it's actually line 3 happens only if it's false. Right after that else, I can add additional conditions. So if, and here I'm going to say if the temperature is greater than 70, that's a greater than sign, and then that's the number 70. Apologize for the messy handwriting, which is equivalent to putting another decision block here. And if that's true, then you're going to execute this block. And if that's false, it gets its own else down here. Okay? The important thing is, if you ever reach this bit of code, then temp is greater than 70 and also temperature is greater than 90. Every other condition on that path must also be, actually, hold on a second. This must be true and this must be false. See what I mean? So you can follow the path back to figure out what exactly the conditions are. Temp greater than 90 must be false before you get here, and then true for there. So, so here we have else if temperature is greater than 70, then we're going to say that this is wear short sleeves, right? So here you wear short sleeves. Forgive the spelling. Here we're going to say write wear short sleeves. How do you spell sleeves? Okay. And you can chain these together. So if that's false, I could have another else if. So that else only happens if it's false, and I can add optionally if I want to another condition. So here my condition is if the temperature is greater than 50. I'm going to write T greater than 50 because I'm too lazy to write temperature. If the temperature is greater than 50, if that's true, then I'm going to say a light jacket. I'm following along with your code, and here. So you see this is two different ways to represent this same process. Here we've got pseudocode, which is nice because you can kind of type this out and write it, and here we've got a picture. Right? So we can add another condition if the temperature is greater than freezing, then we're going to want to say wear a heavy coat, right? So here that corresponds to, this is the false branch, temperature greater than 32. If that's true, wear, I'm just going to write the word heavy coat. And finally, here we see it's possible that this condition was false as well. Then we're going to say else, and we don't put a condition here. We just put here stay inside. So here we got false stay inside. So if I number these 5, 6, 7, 8, 8, 9, 10. Imagine that we were doing something out here. If we were doing something out here, we could write one more line, like 11. Goodbye. Sometimes it's fun to print goodbye at the end of a program, just so you can make sure that it actually finished, right? So if we look at what happens, no matter which branch of code I take here, I'm always going to write goodbye at the end. So if the temperature is greater than 90, if the temperature, let me use another pen. If the temperature is greater than 90, then I'm going to say where shorts, and the next bit of code that I execute, I'm not going to go down any of those else blocks. The next bit of code that I execute is going to be this one that says write goodbye. And by the way, that was using both hands at once. Isn't that awesome? If the temperature is not greater than 90, then I'm going to come down and I'm going to evaluate this condition. If the temperature is in fact greater than 70, I'm going to write where shorts, and then again I'm going to continue down to say goodbye. Right? Now suppose the temperature was not greater than 70. I'm going to check this condition. If it's true, then I print that message, and then I move after this entire selection construction, right? So each one of these is going to branch down to say goodbye, and then execution continues. So this little chunk of logic, if you can trace the execution as paths down this chart, corresponds to this bit of code using a combination of if, else if, to add new conditions that are only evaluated if the previous one is false, and then finally else. That means every other condition previous to it is false. This is called branching. As you can see, according to this picture, it looks like little branches coming off of kind of the spine or the main sequence of instructions. You have these branches that come off of it. The assembly language mnemonics we've seen are branch if equal to, and branch if less than, for instance. They all kind of include that branch notion. And this is where your flow of control becomes in some way nonlinear. In pseudocode, we don't branch to arbitrary places. In pseudocode, we always try to limit the way that we branch, because sometimes the flow of execution can begin to look like this. And this is called spaghetti code. Can I spell spaghetti? I don't know. And it's a result of unstructured branching. So you have all these decisions that just jump and they branch to arbitrary places in the code, and it's unreadable. So what we prefer to do is we limit our branching to special flow control constructs like if and else if and else. All right? So these allow us to select only one of options A, B, C, D, or E to execute. So we're selecting between options A through E. One of those will get executed. And then, of course, execution continues afterwards. Possibly not the most complex idea, but it can be challenging to do something like, for instance, determine whether or not... so here's an analogy that I always like when I'm teaching this concept. If you're familiar with the old coin sorters, you would have a situation where you would drop maybe like a quarter into a slot, and that quarter would go in and it would kind of roll down this way in the coin sorter. And your coin sorter would be arranged with little bins. And if the quarter was big enough, was small enough, so if you dropped in, say, a dime, that dime would roll down and it would fall down into the space that was big enough for a dime. It's hard to see what I wrote because it's the projector itself is in my way, right? But if instead you drop a quarter in, that quarter is too big to fall in the hole, so it continues further down, right? And you can have a hole that is sized right, maybe just a little bit bigger for a nickel, which is bigger than a dime for some reason with U.S. currency, and maybe finally at the end, one that's for a quarter, which is finally where that quarter would fall in. And if for some reason you got a silver dollar, which is bigger than a quarter, and you were to drop that in, the coin sorter wouldn't recognize it, and I guess you'd fall off in here into the else bucket, right? And maybe that's the way to think about it. If any of these previous conditions could have handled it, you'd have fallen into that trap. Okay? So by the time it hits the 5 cents bucket, you know that it's not a dime, because if it is, it already would have fallen into the dimes hole. Okay? Now when you're designing these selection statements, it's easy to make a mistake. You often see people that do the equivalent of making a coin sorter that looks like this. They get the coin sorter right, you know. They set up their statement so that first they try to check if it's a quarter, and then they try to check if it's a dime. And the thing doesn't work, because every time they try to put a dime in, they put their 5 cent thing in, it falls into the quarter bin, right? They check the wrong condition first. So it's possible to get this kind of construction completely wrong. For instance, if the first thing that they checked was whether temperature was greater than 32, then it never ever would have executed any of these conditions. And you can try to check it to convince yourself that that's true. You need to choose the order in which you make your tests appropriately. Okay, and that kind of wraps that one up. The next time I'm going to talk about loops and repetition.